Now before we do as I promised and calculate the z-values for these two positions, we're going to actually go ahead and construct our normal curve. We still have the same double labeled z and x axis, same as we have here. And we have our x equals 2 and our x equals 6 positions here. Now, there's some calculations up here, but we can ignore those for a minute. Between the x equals 2 position and the x equals 6 position, we make an estimate, because I really want you to get in the habit of drawing this thing and making an estimate before you start mucking around with z-values in z-tables. Because your estimate, if you practice this and do as I say, and everybody seems to be doing pretty well with this, your estimate is likely to be reasonable. If your estimate agrees reasonably well with what you get when you do all the z-values and the table and all that stuff, then chances are you did it right. But if your estimate is like 20% and you go to your z-table and you get 70%, then you did something wrong. Either you made a bad estimate or you screwed up the z-table. I want you to get good enough at making estimates that you don't make really, really bad estimates, that you're not going to estimate a 20% when it should be 70%. Okay? So if you can reasonably, reliably estimate a 20%, and then go to the z-table and get 70%, you know you probably messed up something with the z-values, so you need to go back and debug that and correct your result, and hopefully learn to do the process without making errors. Okay, so if we put x equals 2 here and x equals 6 here, x equals 2 pretty close to 0 but somewhat to the right, and x equals 6 between z equals 1 and z equals 2 but closer to z equals 2, we're going to get a picture that looks something like this, and we're going to estimate this area. Okay, well, estimate of this area, 40% is a reasonable estimate for this area. Okay, now it might be 38%, it might be 43% if we drew it with complete accuracy. If we actually measured all these areas, you know, it could come up between 35 and 45%. That doesn't worry me. We got a reasonable ballpark figure here. Okay, now, after doing that estimate, we want to find our z-values for x equals 2 and x equals 6. Now there's a formula for that, and if you're good at using formulas and remembered formulas, have at it. But the numerical reasoning, you might find the numerical reasoning in the picture easier to use than the formula. And if you have both the picture with the numerical reasoning and the formula, then you can reconcile the two and be pretty sure whether you're doing things right or not. So let's just consider, let's find the z-value for x equals 6. Okay? Now, we've estimated that's around 1.6 or 1.7 from my picture. And we don't have a lot of confidence in that estimate, but we know it's between 1 and 2 someplace, because x equals 6 is between 4.4, which is where z equals 1, and 7.4, which is where z equals 2. Okay, well, let's figure out how far x equals 6 is from our mean. That's going to be relevant to our z-value. Okay? Well, from the mean to x equals 6, the distance is, well, and I'm looking at what I have here. I thought I had a calculation here. I've just got a number. The distance from 1.4 to 6 is 6 minus 1.4. Convince yourself of that. You know, what's the distance from 4 to 10? Okay, well, if you subtract 4 from 10, that gives you the distance from 4 to 10. And I hope that the overuse of calculators hasn't removed that bit of understanding, which you almost certainly had when you were in the upper single digits of age before you started using a calculator for everything. So that should make sense to you, that we would subtract the 1.4 from the 6 to find out how far 6 is from 1.4. And we get 4.6. 6 minus 1.4 is 4.6. Okay? Now how many z values is that? Well, a z is 3. So we got to go 3, and then we got to go a little bit further. We don't go 3 and another 3. That would take that would be a distance of 6, and we'd be beyond x equals 6. But if we go 3 and then part of another standard deviation, in other words, 3 is a standard deviation. So if we go 3, we go 1 standard deviation, and then we go part of another one to get out to x equals 6. We can calculate that. We simply divide the distance from 1.4 to 6, which is 4.6, by the standard deviation 3, and we get 1.53. So that's our z value. Okay, so the z value is how far it is from here to here, divided by the standard deviation. That should click. That should make sense. But again, as the curriculum has bypassed thinking with the calculator, might not be so. Try to understand that if you don't see it right away. Okay. Now I've written that out. I've said delta x. Delta x is the change in the x value, and that's from here to here, from the mean where x equals 1.4 to 6. Our displacement from here to here is 6 minus 1.4, which is 4.6. So our z value is that displacement divided by 3. 4.6 divided by 3, 1.53. Okay, and I've got another statement here. Standard deviation is 3. From the middle to x equals 6 is 4.6. How many standard deviations is 4.6? Well, if the standard deviation is 3, then the number of standard deviations in 4.6 is 4.6 divided by 3, or 1.53. Okay, well, we get that. Now, we can do the same thing with x equals 2, and due to space limitations and so forth, I didn't write it out, but I can say it pretty easily. From 1.4 to 2, how far is that? Well, we could count it on our fingers. 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2. Incidentally, there's some recent research that says counting on your fingers really is a good thing. Kids counting their fingers learn their math better because they have a tangible connection with the mathematics. It has meaning. And there's probably more to it than that, but that's kind of what it comes down to, I think. So, nothing wrong with counting your fingers. Well, I got 6. 6 what? I was counting by tenths, right? So that's 6/10. Of course, if you do 2 minus 1.4, and you should do that without a calculator, you get 0.6. You shouldn't need a calculator. Just subtract 1.4 from 2. And if you do, you need to do more mental arithmetic. Okay, well, so the displacement, the delta x, the change in the value of x from here to here is 0.6, and the standard deviation is 3. If we divide 0.6 by 3, we know how many standard deviations then. And that's going to be our z value here. Well, 0.6 divided by 3, and you can count to 3 by 0.6, as it takes 5 0.6s to go into 3, so 0.6 is 1/5 or 2/10 of 3. Again, numerical reasoning everybody should understand. One way or another, you can divide 0.6 by 3 and you get 0.2. So z equals 0.2 here. Now I'm not sure I actually labeled that on the graph. I said what to look up, so it might be a good idea to go ahead and do a little labeling here. Okay, so x equals 2 occurs then at z equals 0.2. That might be a little hard to read, especially since I kind of screwed up that circle. That says z equals 0.2. It corresponds to x equals 2. And x equals 6 corresponds to z equals 1.53. Again, a little hard to write clearly with the chalk in the space I left myself there. So that would be here and this would be here. I'm not going to try to draw an arrow. We want to find this area, okay? So how do we use the z-table to find this area? Z-table gives us the area between the middle and our z value, okay? So the area from the middle to x equals 2 is what? Well, if we look up z equals 0.2, we find out. If we look up z equals 0.2, we see that the area from the middle to x equals 2 is 0.079. Okay, now that would correspond to the area of this region. Now we want the area of the region shaded between x equals 2 and x equals 6. Okay, well, we can also look up the area from the middle to x equals 6. And we find that that's 0.437, meaning it's 43.7% of the total area, or 0.437 of the total area. So, from the middle to here is 0.079 of the total area. From the middle to here is 0.437 of the total area. I think I might have said 436 once there. Got a 6 in my head. So from here to here is 0.436. From here to here is 0.079. So what do we have from here to here? Well, the region from here to here is the region from the middle out to here, minus the region of this strip from here to here. So if we subtract the 0.079 that indicates this area from the 0.437 that would indicate the whole area from the middle out to here, we're going to get our result. And I think I've done that up here someplace. Yeah, here we go. So this area has to be the 0.437, the area from the middle to 6, minus the 0.079, which is the area from 0 to 2. And we have to see that. Now you understand why we've made an estimate? Well, one reason we've made an estimate, the 40% here, is because we might have accidentally tried to add these two numbers. That'd be an easy error to make. And if we add these two numbers, we get over 50%, and we know that we don't have over 50% between x equals 2 and x equals 6. We know that from our picture. We know that because from the middle on is 50%. So we use our estimate, and it wasn't all that close. This comes out closer to 0.035, 35% than 40%, but still we have something to guide us and make sure that our result is reasonable.